Have you ever noticed how South America and Africa seem to fit together like puzzle pieces? If you look closely at a world map, the coastlines of these two continents appear to align almost perfectly, as if they were once joined. That's no accident, it's a clue to Earth's ancient past. For centuries, explorers and scientists wondered about this striking similarity, sparking curiosity and debate about the origins of our continents. Hundreds of millions of years ago, all continents were joined as one supercontinent, Pangaea, surrounded by a vast, endless ocean called Pangaea. Imagine a world where all land was connected, forming a massive landmass teeming with ancient life. The world map we know today is just a fleeting moment in a long story of shifting continents. Over millions of years, the land has been in constant motion, slowly drifting apart and coming together in new ways. In 1912, a German meteorologist named Alfred Wegener proposed the radical idea of continental drift, suggesting that continents move across Earth's surface. His theory challenged the established beliefs of his time. Wegener believed today's continents are fragments of Pangaea, which began breaking apart about 200 million years ago. He gathered evidence from fossils, rocks, and ancient climates to support his theory. Yet his theory was dismissed for decades because he couldn't explain how continents could move. Many scientists were skeptical, and his ideas were met with resistance and even ridicule. The breakthrough came after World War II, when sonar mapping revealed dramatic features on the ocean floor: mountain ranges, trenches, and volcanoes. These discoveries hinted at powerful forces beneath the surface. These findings provided the missing evidence, leading to the revolutionary theory of plate tectonics in the 1960s. Scientists realized the Earth's crust is broken into plates that move and interact. Plate tectonics not only confirmed continental drift, but also explained the powerful forces driving it: earthquakes, volcanic eruptions, and the creation of mountains. Wegener's vision was finally vindicated, transforming our understanding of Earth's dynamic nature. His persistence paved the way for a new era in geology. The continents are still on the move, shaping the planet's future as they have its past. Our world is ever-changing, and the story of continental drift continues to unfold beneath our feet. Wegener's theory wasn't just about matching coastlines. He believed the Earth's surface was dynamic, not static, and that continents had slowly moved across the globe over millions of years. To support his revolutionary idea, he gathered evidence from fossils, rocks, and ancient climates, searching for clues that spanned continents and eras. Identical fossils, like the freshwater Mesosaurus, were found in both South America and Africa, separated today by a vast ocean. This was impossible unless the continents were once joined together, allowing animals to roam freely across what are now distant lands. The ancient fern Glossopteris appeared across South America, Africa, India, Australia, and Antarctica, its remains scattered across the southern hemisphere. Its heavy seeds were far too large to drift across oceans, suggesting the continents were once connected in a single landmass. Mountain ranges such as the Appalachians in North America and the Caledonians in Europe line up perfectly when continents are reassembled, forming continuous belts that stretch across oceans. Geological similarities, matching rock types and structures across continents, further supported their former connection, hinting at a shared geological history. Evidence of ancient glaciers in now tropical regions, such as striated rocks and glacial deposits, revealed that these continents once lay closer to the South Pole. And coal deposits in Antarctica, formed from lush forests, showed that continents had shifted through dramatically different climate zones over time. These clues, fossils, rocks, and climate indicators, painted a clear and compelling picture of a world in motion. Over millions of years, continents have drifted vast distances, reshaping the face of the Earth. Wegener's evidence was compelling, even if the mechanism behind continental drift remained a mystery for decades, puzzling scientists for generations. Today, we know the story of continental drift is written in the rocks beneath our feet, waiting to be discovered by those who look closely. The theory of plate tectonics finally explained how continents move. Earth's outer shell, the lithosphere, is broken into rigid tectonic plates that float atop the semi-fluid asthenosphere. Heat from Earth's core drives convection currents in the mantle, slowly shifting these plates. At mid-ocean ridges, magma rises and forms new crust, pushing plates apart, a process called seafloor spreading. The Atlantic Ocean widens as North America and Europe drift apart, while the Mid-Atlantic Ridge marks this ongoing separation. Old crust is destroyed at subduction zones, where one plate sinks beneath another and melts back into the mantle. This cycle of creation and destruction powers earthquakes, volcanoes, and mountain building. Plate tectonics is the engine behind Earth's ever-changing surface. The continents ride these plates, drifting at the pace of growing fingernails. Our planet's surface is in constant slow-motion transformation. The action happens at plate boundaries, where plates diverge, converge, or slide past each other. At divergent boundaries, plates pull apart and new crust forms, like at the Mid-Atlantic Ridge. Convergent boundaries see plates collide. Oceanic plates subduct beneath continents, forming trenches and volcanic mountain chains like the Andes. When two continents collide, neither subducts easily, so the crust buckles upward, creating massive ranges like the Himalayas. The Indian plate's collision with Eurasia is still pushing the Himalayas higher today. Transform boundaries like California's San Andreas Fault occur where plates grind past each other, causing earthquakes. These boundaries are hotspots for geological activity, earthquakes, volcanoes, and mountain building. The relentless movement of plates shapes the planet's most dramatic landscapes. Understanding these boundaries helps us predict and prepare for natural disasters. Earth's surface is a patchwork of restless, interacting plates. Pangaea wasn't Earth's first supercontinent, nor will it be the last. Earlier supercontinents like Rodinia and Pangaea formed and broke apart over billions of years, reshaping the planet's geography and climate. Rodinia, assembled 1 billion years ago, eventually fragmented, possibly triggering a global ice age. Pangaea followed, briefly uniting land masses before splitting into continents like Laurentia and Gondwana. This supercontinent cycle, driven by plate tectonics, influences sea levels, climate, and evolution. Understanding this deep history helps us glimpse Earth's future. By tracking the slow but relentless movement of Earth's tectonic plates, scientists are able to predict how the next supercontinent might form over the next 50 to 250 million years. These predictions are based on a combination of geological evidence, computer simulations, and our understanding of how continents have shifted in the past. The most likely scenario, called Nova Pangaea, imagines the Atlantic Ocean continuing to widen while the Pacific slowly closes. In this vision of the future, the Americas eventually collide with Eurasia and Africa, forming a vast new landmass that stretches across much of the globe. In the Pangaea Ultima scenario, the Atlantic reverses course and begins to close, pulling the Americas back toward Europe and Africa. Over millions of years, the continents reunite around a shrinking ocean, echoing the ancient supercontinent Pangaea. The Orica model offers a different twist, both the Atlantic and Pacific close, while a brand new ocean forms as Asia splits apart. In this scenario, Australia drifts northward and becomes the heart of the new supercontinent, surrounded by reconfigured landmasses. Amasia, another possibility, envisions all the continents slowly drifting northward to cluster around the Arctic Circle, leaving Antarctica isolated and alone at the bottom of the world. Each of these scenarios depends on how subduction zones, rifts, and the deep forces within Earth's mantle evolve over time, shaping the planet's surface in unpredictable ways. While these models are speculative, they remind us that Earth's surface is far from settled. The continents are always on the move, and their future arrangements are still being written by the forces beneath our feet. The continent's slow-motion journey will eventually create a new supercontinent, its exact shape and location still a mystery, waiting to be revealed by time and tectonics. Our planet's future map will be as alien and unfamiliar to us as the ancient world of Pangaea is today, a reminder of Earth's ever-changing nature. The story of drifting continents is far from over, and the next chapter is still unfolding beneath our feet. Earth is a restless planet, its continents in constant motion. Plate tectonics has transformed our view of the world from static to dynamic, revealing the forces that build mountains and trigger earthquakes. These same forces create fertile soils and beautiful landscapes, but also bring natural hazards. Understanding plate boundaries helps us prepare for earthquakes and volcanic eruptions, making our world safer. Human history is a blink compared to the slow dance of continents. In millions of years, today's map will be unrecognizable. Continents merged, oceans vanished, new mountains rising. Studying Earth's tectonic journey connects us to a vast past and an unimaginable future. Our planet is, and always will be, a world in motion.